Section 10.3 is displaying data part 2. The first data that we're going to look at in this one is a line graph. A line graph is just line segments that connect one data point to the next, and they typically show how something changes over time. We want to think of this like connect the dots. All right, so we'd already started this particular graph, so let's go back in and talk about, we're using the horizontal axis as our days of the week because that's the part that we don't have any effect over. It's the independent variable. And then our dependent variable, our vertical axis, is our number of hours spent studying. And we had labeled, or I had done labeling for the days of the week on the bottom, hours studying on the horizontal, or the vertical, excuse me, and we had plotted points on Monday and Tuesday, respectively. And now we're on Wednesday, and we're plotting it at 0.75. Thursday is 2 hours. That's pretty close. Friday is at 0.25 hours. Which, honestly, that's probably a bit optimistic, don't you think? Saturday, also optimistic at that 0.25 hours. And then Sunday, we get serious about it again, and we've got an hour and a half. You guys know how it goes. I'm not saying anything that's not true. Okay. So we're going to connect the dots over time. So you're doing straight lines. I will say that one of the things that I look for when I grade these, both homeworks and for tests or whatever, is the lines need to really look straight. So grab some kind of straight edge. You're going to need it for something else here in a little bit later anyway. So your ID card, a note card, something that will allow you to make a fairly straight image between the two. The nice thing about an iPad is that I actually have the ability to make those straight images as well. So I can do mine just like you are. Okay, I skipped one. That was not good. No, I didn't. That was it. All right, and so you're just connecting one to the next over time. So I want to connect each of the days of the week's hours. And my graph looks something like this. And that's a line graph. Have you guys seen a line graph before? Yeah. They occur all the time in like popular culture kinds of things, media kinds of things. Where maybe have you seen a line graph used? Can you think of a specific example? Economics. Economics is really popular. Can you think of an example within economics where you might have seen it used, Hannah? Stocks and bonds, yeah, things like that. The stock exchange, those are often shown with line graphs. They want to see all the crazy volatility of something and whatever. Yeah, you can look at that. Any company in general is like profit over time, things like that. When they're wanting to expand or to consolidate, they'll look at those kinds of graphs and those kind of numbers to give a general view over time. Now this one isn't really over time in that same way, but it does give you sort of a picture of what's happening in a given week. Okay, the ebb and flow of studying times. Any questions on this one? Okay, because the next one's about to get quite interesting, as you can see by your picture on your page. Scatter plots. Scatter plots are often used when the relationship between variables cannot be easily depicted even by a broken line. Now sometimes it can be depicted by a broken line, but you just wouldn't want to for some reason, or it doesn't make sense maybe to you, or it's just as easily seen by looking at the dots themselves as opposed to connecting them with a line. Okay? Now the next example that I have, I'm going to actually graph it on an actual grid because it's going to be a little bit easier, I think, for us to see visually. You've got a big chart, right? Lots and lots of information. So let's kind of take a look at this one. And this is one where I've actually changed this time around when I'm teaching this because I think it'll match up a little bit better with the kinds of graphs you're seeing in your textbook for this. Okay, Coach Lewis kept track of the vertical jump heights of his starters over the past 8 years. So he has 5 starters, first through 5th place starter or something like that. And then these are his how high his people can jump. And I don't write this in here. I apologize. It's written on my paper, but I didn't get it written in here. This is in inches. His height in inches. Yes, I think I changed it on yours because I realized I had put 7 and decided that was enough, and I forgot to change it on the iPad.
And
Thank you.
The 5th starter in 2002, on ours it's 58.
Okay. We will change that to match yours as well. These tables are not copy-pasted, so you know what? Let's just take a minute, everybody. Check what I've got against what you have on your screen so that we do have, in fact, the same thing, because I did enter all these second values into my iPad separately. rest of them look okay? Okay, fabulous.
Oh,
You know,
wait,
oh.
oh, wait.
Okay, 1 out of 35 is not too bad, right? That's like a 0.3%. I mean, that's like 3% error. 3%, that's not bad. I'll go with that. Okay, all right, so here's what we're going to do, is we're going to create, basically like we did with the line graph, we're going to create the dot picture graph of this, okay? And it's going to look a little bit funny because there's a lot of it, right? And so let me just kind of show you what mine looks like on my paper, and then we'll get into actually creating it on yours. Okay, I've got an extra line in the middle of this thing going on, so just ignore the line from it. But do you see all the dots? That's what we're going to create. Okay? So I'm going to actually pull up a screen in here where I have access to a grid. I think a medium grid's probably big enough. Okay, and we're going to do just like we did before. We're going to create that X and Y axis, or that horizontal vertical axis. And we need our years to be separated out, and we need our vertical jump heights to be separated out. But we're not going to start our vertical jump heights at 0, because none of my values are anywhere near 0, right? And we're not going to start at the year 0, because we're in the year 2000 something or other, and it doesn't make sense to start in the year 0. So both my horizontal and my vertical axis aren't starting at 0, 0. Does that ever make sense of that? So there's a couple things we have to do when that's the case to make sure that whoever's looking at our data is aware that we know and we fully intended that it didn't start at 0, 0. What we do is we do a break in the line. And so, whoops. You typically would erase a part of the line. I don't know if I can erase part of my line. I can, actually, so let me do that. So you do this sort of a break in the line, and you do it both on the horizontal and the vertical, because we've done it in both places where we're not going to actually report the data at the exact same way. All right, we do want our graph to have values that make sense to us, though. So we actually might put, even though we don't have data for it, the year 2000 on there. It's awfully close to the data that we have. Do we have to start at 2000? Well, we don't have to, but it's not unreasonable to think that we would. I need the year 2002 for sure on there, right? Because I have data for 2002 all the way up to 2008. So I'm just going to skip my values because the grid has the ability to do that. This is 2001, and then this one's my 2002, and then I have 2003, and then I have 2004. So I'm making my grid so that it's not 1 unit equals 1 value, just because I have the space to do it. I didn't mean 5 there, I meant 6 there. 6, and then 8. That was my last year, wasn't it? Okay, what is the smallest jump height that we have recorded in our data? 58. 58, and what's the largest? 77? 58 up to 77. So I need to at least start at 58. So I will start just at 58. And I need to go all the way up to 77. So I kind of like the idea of doing it in increments of 2s. So I'm going to do this. I'm going to label it every 2. To do a shift on my graph, so I'm going to shift my graph down a little bit because I'm running out of space. So you can't do that on chalkboard, right? Can't shift my graph down. Or on paper, yeah. Oh no. All right. I need 2 more, don't I? We're going to try this. Oops. We're just playing around. It's all fun, right? Does that get me exactly what I need? 77, right?
Yeah.
Okay. One way or another, we'll make it work in there. I have no idea what happened with my erasing down here. Apparently I erased something. That wasn't what I wanted to erase at all. Let's just draw back in. Okay. It's close. We're going to plot a whole bunch of points. You guys ready? All right. So I want you to go through. I want to go through, and we're going to get all of these points plotted at the correct year. So in particular, if we go year by year, it's not too bad. 2002, I have 65. Okay, let me get a dot going on here. 60. Where's my 2002? There we go. 65. 63, 60. 62 and 58. Awesome. 2003, I have 67, 65. 64, 66. 62. 2004, I have 67, 68, 66, 64, 65, 66, 67, 68. Look at that, just right in a row. That's fun. Uh, 2005, I have 65, 66, 67, 68. And 70. 2006, I have 66, 67, 68, 69, 70. They're getting taller, or taller jumping. (2007) is 69, 70, 72, 73, 74. 69, 70, 72, 73, and 74. And last year, 70, 71, 72, 75, 77. 70, 71, 72, 75, and 77.
What if there was like an overlap, like for 2002 there was like two 65s?
You just would only see one of the points. Yeah, I mean, I've contrived the data. I created it, right? So I didn't do any overlaps, but yeah, if there were an overlap, it would just be on top of it. We just wouldn't see both points. Yeah. All right. We need to label a couple other things. What else do I still need to label? Oh, you know what? I forgot something, and you guys didn't tell me I forgot it either. Oh my goodness. What did we forget? A title. Let's fix this. What should the title be, or what could the title be over here? Average study times for students or in a given week or something like that. Okay. We need to do that on the one we're on right now, which is what made me think we hadn't done the other one. What is this graph's information telling us? These are vertical jump heights. That's fine. We could say, if you want to, I didn't actually have this kind of information last time, so let me put it in here that we could actually say this. We could say from 2002 to 2008. You don't necessarily have to. It's reflected in your horizontal axis, but you could describe it that way a little bit more specifically. I do also need to do one more thing. I need to label that vertical axis. So what is this vertical axis? This is the jump height in inches. All right, vertical jump height in inches. This is what a scatter plot looks like. Now, the ones that you're going to be working with primarily, the plots are already going to be created. So you're going to start with a picture of crazy dots everywhere. And they don't always line up so nice and neat and pretty, of course, and stuff too, but they've got a bunch of dots on a screen. Okay, so obviously this doesn't make any sense to connect lines like the connect the dots thing. Agreed? I mean, it doesn't even make any sense to talk about it like that. And so that's where scatter plots are useful, is with data like this, where it doesn't make sense to connect the dots in a way like that. That said, it could be a graph where you could actually connect the dots as well. All right, so we had our information. It asks us the question about what kind of association is there for the data. So we created the graph. That was good. But then it asks about association for the data. Association for the data means as you're looking at the data from left to the right, okay, what is the graph doing? Is it overall increasing, or is it overall decreasing, or is it overall just sort of bouncing around, leveled out, kind of flat? You know, there seems to be no increase or decrease. So what does this graph appear to be doing? Increasing. Overall, it's sort of moving upward and to the right, right? Over time. So this is called a positive association. And you can think of it as a positive slope as well. If we were to somehow connect this in some fashion, I don't know, with like a cloud or something like that, it would have this positive movement as a positive slope kind of a way. So there's a positive association. Now, while we can't connect this with a line graph, we can connect things in such a fashion or give it a line. It's a trend line. So that's the next one we're going to look at, is something called a trend line. A trend line is a line that closely fits the data and can be used to describe it. You will also hear this word, the words used, best fit line instead of trend line. Okay. Sometimes you'll hear, it's going to come to me later. There's another phrase that I sometimes hear with it used as well, but least squares line, the line of least squares. That's something you'll hear sometimes too. So we're going to look for least squares. Yeah. What you're trying to do is you're trying to minimize how far away the line is from each of the dots by taking the squared distance between them instead of using the distance between them. So that's actually how you would actually mathematically create this. We're not going to be trying to mathematically create it. We're going to try to be approximating it, which is just fine for what we're doing. Okay. So what we're going to do is we're going to use the data that we just created the wonderful picture for, and we're going to create a best fit line for the data. After we do that, we're going to estimate the equation for that line that we created. Okay, so that's a different kind of a question. And then we'll see maybe why I wanted us to put in the year 2000. All right, so let's take a look. Here's what we're going to do. We're going to try to draw a line. Our line is just a plain old line. Okay, so not line segments like my line graph. It is a line. It will be straight, and your graph needs to look straight. Okay, like when I ask a question on this on the test, if the line doesn't look straight, you're probably going to get to redo the problem just for not making a straight line, because that's how important it is. Okay, so your goal is to draw a line so that it kind of looks like it balances out the number of dots above and the number of dots below. That's really what it is. You're trying to make a balanced looking line through the data. It has the same kind of a sloping pattern, or a slope, right? But it kind of balances out how far away things are. So your line might look something like, that's probably okay. It might not look quite that steep. You might think it looks a little bit more like that, because really it doesn't get very close to that really tall one, but it doesn't get really close to that very short one. There's some error in what I just did, right? I just drew you two lines that both seemed reasonably accurate, but they weren't the same line. And if I got you equations for each of them, they wouldn't be the same. So there's going to be some flexibility in your answers and my answers, and we're all going to be okay with that, right? However, this is our best fit line, or our trend line. When we do lines, we should really put arrows on the end. That's an appropriate kind of thing. but we want to find the equation of this line now. Okay? Now, the equation of the line may or may not include points that are in the data. This one actually probably will. Mine does anyway. Mine looks like it actually hits some of these points, right? There's a couple of them in here, 3 of them, that it actually looks like it flat out goes right through. When you create a trend line, it sometimes doesn't look like it goes through any of the data points exactly. That's okay. There's nothing wrong with that. But when we create a line, we actually have to do that using a couple of different options. Tell me what you remember about creating equations of lines. How can you do that when you're given a line? Okay, so change in y over change in x, what is that calculating? Do you remember? Slope. So you can look for 2 points, and you could calculate the slope of the line. That's something that's going to be very useful for us. So we're going to do that. What else do we need besides the slope to have a line? We need what? A point. And it could be any particular point. It could be a very specific point, the Y-intercept. It depends on what the kind of information is that we're looking at. Here, it doesn't really make sense to do the Y-intercept as such because I had these weird breaks in the graph over here, right? I mean, like, my y-axis is not like your 0 or anything here, right? So probably just some other point in the graph would probably be reasonable. In particular, I'm going to show you how to do something that makes it a little bit easier. We're going to take this year 2000 as a starting point in something, and we'll go from there. So first, let's find the slope, like Haley suggested, by taking 2 points on the line. So I'm going to take 2 points in my line. You don't have to necessarily take the points if they aren't on your line. Select 2 points on your line. I'm going to pick this one on mine and this one. And again, I don't have to pick the points on the line. If I really wanted to use it, I could use this point right here, right? That's the line. I could use that ordered pair, and that'd be okay. There's nothing special about which ones we pick. We should get the same slope no matter what we hit, or a very close value to it. Okay, so I'll do the work here so we don't lose the data. Haley mentioned it's the change in y, so it's y2 minus y1, over the change in x, x2 minus x1. If you've drawn it on a grid, which I happen to have, you could count instead of actually doing the subtraction. You do need to be careful because down here my years are 2 boxes wide, right? Not just one, so you would have to be a little bit careful on that. But let's just figure out what years corresponded to my blue circles that I've got on my screen currently. What are those years? 2003 and 2005. Okay, so those are my x values or my y values? They're my x's. I was about to agree with you, Emily. They're my x's. Okay, so the years are the x values, and I'm going to do the later value minus the earlier value. Not because I have to, but I mean, I got to pick something. I might as well go with what I am going to do to get a positive value. Now, I need the corresponding y values, which are the height values of those 2 points. So in 2003, that's the first blue circle on the far left, what was the vertical height of that particular point? 64, right? So that needs to be above the 2003 value, 64. The 2005 value, so going above the 2005 value, my formula came from here. What's the vertical height here?
67.
That's 67. Okay, so what happens when I take 67 minus 64? I think I get a positive 3. Do you have yours in the backwards order maybe?
Oh, yeah.
It's okay. When we're done with this, we want to make sure that the slope that we're getting matches what we think we should be getting. So if we did put negative 3 down and we looked at it again, we'd be like, oh, wait a minute. There's an error. I know this slope is positive, so we would check that later. And then I have 2005 minus 2003, which is 2. So my slope is 3/2. Or if you really don't want to do the fraction, you want to write 1.5, that's cool. Okay, so when you made your calculation, you may not actually get 3/2, right? That's possible. You may get 1.67, which would be 1 2/3, right? 5/3 is what that would be. You may get something that's like 1.1 somehow, with the values you pick. Your value may not look the same, but there are things that probably won't equal. If your value is 3, twice as much as mine, there's probably something weird going on. You probably either didn't draw the line right or you didn't calculate the slope right. Okay? So there is some error in what we can do, but there's also some point where the error is too much. So be careful about that. This is just the slope. I need a line. So let me go back over here where I had the space to do it. Oops, that was it. We found out that m was 3/2 or 1.5 or some close value to that. And do you remember the general equation for a line with a point in it, like Emma had suggested? Okay, y equals mx plus b has a point in it that's specifically the y-intercept. There's another equation that we might want to use instead. It's okay. It looks like this. Y minus y1 equals m times x minus x1. The nice thing about this is that instead of specifically needing the y-intercept, which is what the other one needs, the way it's even kind of written, is that I can pick any x1, y1 pair, and that's kind of nice. Okay. All right, we have a couple of options here. Let us actually create one option that is probably the natural one for writing down. And then we'll create another one that's a little bit easier to work with version of it, but you have to think a little bit differently on how you're creating it, okay? So here's the first one. Let's actually pick a ordered pair, and maybe it's one of the circled ones that I picked. We could use that. That'd be fine on our graph. So since we've already found these points, let's just use this first one, 67 and 2005, okay? So that's my x1 and my y1 in my equation. So I have y minus y1. What was the y1 value? 67. The y values are the heights. The x value is the 2005, though. So the m is 3/2 times x minus 2005. We're going to simplify this. We're going to clean it up. We're not going to leave it, in this fashion. But this would be y equals 3/2 x. What happens when you multiply 2005 by 3/2? You're going to get a decimal. Can somebody give me a decimal expansion for that? Just for the moment.
3007.
We'll use all decimals since I'm about to get a decimal in this anyway. 3007.
0.5.
And then what's going to happen with that 67 that I did not write on the other side of the equation at this point? I'm going to add it to this side. So this is now y equals 1.5x minus what? It's still minus 2,000 something.
2,940.
Awesome. Now, in order for this to make sense, and this is what this note is below this, you have to have some verbal language along with this that tells you what in the world does x and y mean in this equation. So what was x in this equation? The year. What is y in this equation? The height of the jumps, right? So in inches, centimeters, what was it? Inches, right? Okay, so this is the inches is what we write first. This might be one of those things you want to write on your note card when the time comes. Inches is what you write first, the output on the y value. And then you have to say how x is measured. This would be in year x, or when x equals the year, or something like that. You have to indicate that x is the year that we're talking about. So on the next part of the problem, we'll do part C and then we're going to come back to this. If this next part of the problem asks you, using my equation, what would we predict the jumping height to be this year, what do we plug in for x? 2015, right? Okay, so this is y equals 1.5 times 2015 minus 2000, what was my number? 940.5. Okay, so the numbers are a little bit bigger than what we're going to do here in a minute, but we just plug in the year exactly like the year looks. What does this give us? Yeah, the total after we're all said and done. It shouldn't be negative. 82?
So you don't multiply the last number by
You multiply these two numbers, and then you subtract the last one.
Okay.
See, this is what we have our equation to be, right? Okay.
So I ended up
Well, it shouldn't still be negative. If your slope is 1, it's still increasing. You're still... I know, but if you're putting in a 2015 and your slope is 1, you should still have something that's going uphill because you're going to add the number 2015 to something else. Let me take a look at it when we're done, Haley. There may be an error somewhere else that you're not seeing.
Yeah. Minus 2000. See, the thing is, if her slope is 1, that times 2015 minus 2000.
But if her slope is 1, then she would have had a different number here at the end. She wouldn't have 2940 because she would have had the 1 multiplied by the 2005 or whatever her year was. So both of those things get affected if your slope is somewhat different. Okay, let me show you another option here. This is not my favorite. I mean, in terms of being able to just plug in the number 2016, that's okay. But this is not really my favorite because the numbers are a little bit weird. I mean, it looks really weird to have this minus 2940.5 at the end. And the reason it feels a little bit weird is because this is sort of measuring the year as though starting at year 0 makes some kind of sense. Oh, the Y-intercept is negative 2940.5. I mean, that's weird. That has no context for what the problem is really doing. So another way to do this is like this. We're going to use all the same information. We're going to enter it in a slightly different way. I'm still going to have y minus 67. I'm going to still have the 3 halves. But instead of having x minus 2005, I'm just going to do x minus 5. Okay? So I'm kind of going to ignore the 2000 part of this. So as I work with this from this fashion, I would end up, I'd move my 67 just like I did before. So this would be y equals 1.5 x. I'd have the 1.5 times the 5. So what's 1.5 times 5? Yeah, which is 7.5, right? Okay, so I'd have minus 7.5. And I'd have plus the 67, because I'd be moving that over. And then what happens when I take negative 7.5 and positive 67? $59.5? Awesome. Okay. So obviously the only thing that's different is the y-intercept at the end, correct? Whatever we're calling the y-intercept. But we got a different y-intercept because we did what? We eliminated the 2000. We used 5 instead of 2005. So how does that change my description? Because that's what's going to change. This is still inches, but x is not the year anymore. What is x?
In 2000.
Say that really loud. It's the years after 2000. It's the number of years that we are after the year 2000. Now I'm going to show you from the graph another helpful thing about this. So this is inches. And I'm going to do this on an angle because I'm running out of space. This is x years after 2000. Now, in measurement, in terms of measuring this and using this, what this means over here is that I would do y equals 1.5. I'll put a value in, and then I'll do plus the 59.5. What value would I put in for the current year? 15. So my numbers that I'm working with are actually smaller if I think of it this way. This isn't necessarily any better, it's just a different way of doing it. I should still get 82. Do I?
Yes. I got 82.
89.5. That sounds to me like you didn't multiply by 1.5, but maybe by something different. 82 is what you got, Emily? And both of these, I didn't write it down, but these are inches, right? You got it? Okay. So the estimation that we're using based on this equation is that it's inches, 82 inches for the year 2015. Okay. One other thing let me make mention of before we move on. Over here, if I'm looking at the year 2000, I'm about right there, right? Does that look like about 59.5? It's pretty close, right? Somewhere between 59 and 60 anyway, yeah? Because here's 59, here's 60. And that right there is the Y-intercept, quote unquote, if the year is 2000, which is what we were looking at. So if you're measuring it since a year that's on your graph, it actually makes the graph's the Y-intercept calculation easier. I wouldn't even have to do all of this here at the bottom. None of this is necessary if I measure it since year 2000. I could actually use this formula that y'all mentioned earlier. I found the M. It was 1.5. Fabulous, or 3 halves. The B value, I can look back at my graph and I can say I'm measuring since the year 2000. So where am I in the year 2000 on my graph? Oh, look, I'm at about 59.5 or 59 or whatever it is you're estimating that you're at. And you can simply plug that number in for B. You do have to be careful, like this note says, to have the language here that tells me how to use your equation. If you don't, then I don't know what I put in for X in the year 2015. Are you with me? How do I know if I put in 15 or if I put in 2015 or if I put in 115 or whatever? I don't know because you didn't tell me. Okay, any questions on this one? Okay. I think we just have one left to do. Yeah. Association. What did we say association actually means in terms of the graph? If it's going up or down, mathematically, what's that word? Negative or positive. Somebody said it. Slope. Hannah said it. Slope. It's all about the slope, right? The graph going up or down from left to right is about slope, or if it doesn't move at all. So looking at these, what the question is when it asks about association is it's asking about slope. So what is the slope on the first equation? -2. So is this a positive, negative, or no association? This is a negative association because the slope's negative. Second one. Positive because there is a positive slope. What's going on C? There's no association. Do you know what kind of line it is? Everybody likes to use the word straight. It's the funniest thing. All lines are straight, right? Horizontal is what I mean. When we say it all the time, I do it too. Horizontal is what you meant, right? Horizontal. So this is no association. And it's because it's a horizontal line. Not increasing, not decreasing. Okay, any questions on that? All right.